Okay. So in the last class we have discussed about the free radical addition reactions where anti-Markovnikov rule is a predominant topic. Okay. So when it is peroxide, the most stable free radical will be the deciding regioselectivity deciding factor. Okay. So the bromine will be going to attach to the opposite or anti to the Markovnikov product. So generally if it is HBr without any peroxide, so then the bromine will be going to attach to the terminal carbon, because when it is a positive ion that is generated, carbocation if it is generated, it will be more stable because of the withdrawing groups. Okay. So in a similar case, if it is peroxide presence is there, then radical formation will also happen. Okay. So with the radical formation, the similar kind of stable radical should be formed. Okay. So addition must be here. Okay. So this would be the product. Okay. So it just if you able to do the questions of the Markovnikov rule, you will automatically able to do the anti-Markovnikov rule. Okay. So just make the reverse of that addition. Okay. Make the reverse of Markovnikov addition, then it's going to be easy for you. Okay. So if at all these two groups are there, just a minute. Okay. If at all the groups which are attached to the double bond are with two different kinds, then it can be unsymmetrical. So which is more donating will be going to give electrophilic addition reaction. So this is simple electrophilic addition reaction because there is no presence of the peroxide. So bromination will be to the more electron rich carbon. Okay. So if this is the case, so it will be aldehyde, which is a withdrawing group. Okay. So here it is a withdrawing group. So if it is a simple electrophilic addition reaction, bromine must add here. Okay. So that it will be more stable. Okay. So it's going to be add here for this case. So it will be the product. Okay. So if it is HCl and peroxide, there is no Karash effect or peroxide effect when it is chlorine. Okay. When it is bromine only, it is going to happen. So similar to electrophilic addition reaction is going to happen here. Okay. So if this is the case, then you can find the Karash effect. So it will be reversed to the Markovnikov product. So here it will be the product. Okay. So just you need to see the vice versa. Okay, whether it is Markovnikov, whether it is anti-Markovnikov. So if we are able to understand the Markovnikov products, and if we are able to do the Markovnikov products, it will be very easy to do the anti-Markovnikov products, because you need to just make the reverse addition of that particular double bonded carbons. Okay, but here it is different when it is trichlorosystems, or when it is carbon tetrachloride or carbon chloroform, okay, bromoform, whatever may be, in presence of the H nu, they are going to give elimination reaction, that is alpha elimination to results the carbon. This we already discussed in the carbon formation. So whenever double bond is there and whenever carbon is there, it's going to give cyclopropanation. Okay. So cyclopropanation, so cyclopropyl ring is going to form. So this is not simple free radical addition. Okay, this is carbon addition, which is electrophile. Okay, so these kind of cyclopropanation reactions are called Simmons-Smith reaction. Okay, Simmons-Smith reaction. This you can also find in the named reaction playlist. Okay, that I have made in the last 6 months back. Okay, so in the last sessions. So Simmons-Smith reaction, okay, where a double bond is going to add by the carbon to result a cyclopropyl ring. Okay, so this is what Simmons-Smith reaction. Okay, so this example is based on the Simmons-Smith. So why I am included means, So you should not follow just single way without looking into the reagent. Okay, so here reagent system is readily going to results into the carbene unlike simple free radical. Okay, so careful. Next, so this is free radical addition reaction which is anti-Markovnikov. So if it is Markovnikov carbocation generation, the benzyl carbon will be more stable, so bromine addition will be going to happen here. So reverse to that, anti-Markovnikov bromine will be going to add here. Okay, so just you need to make reverse. I am trying to give the simplest way of regio selectivity explanation. Okay, so try to follow the same pattern. Okay, so you, if you follow the same pattern, it will not be much confusing. Okay, whether to go for anti Markovnikov, whether to go Markovnikov, you should see only Markovnikov's product only. Okay, and after deciding the Markovnikov product, look into the reagent system. If a peroxide is present, you need to make opposite of that. Okay, so in single step it's going to happen, or it's going to decide whether it is a Markovnikov addition or whether it is an anti-Markovnikov addition. Okay, so the simplest way, try to find out the most stable carbocation. Try to find out the Markovnikov product. After that, if it is a Markovnikov product or Markovnikov reagent, write the Markovnikov product. If it is an anti-Markovnikov reagent, so write opposite to that. Okay, so next one. So here it is also anti-Markovnikov. So just look into the first Markovnikov product. So Markovnikov will be, this is a trifluoromethane. Okay, so trifluoromethyl group which is a withdrawing group. So carbocation must be away from this. So here it is going to form. Okay, so here bromine is going to add if it is a Markovnikov. So reverse to that, as it is a peroxide, so bromine will be going to add here. Okay, hydrogen will be going to add here. Okay, so next, here again carbon formation. So if it is carbon formation, what could be the reaction? It is Simmons Smith reaction. Okay, Simmons Smith reaction, so that olefin is going to turn into the cyclopropyl ring. But the thing is, carbene can be attacked from the above the plane and below the plane. Okay, so which you feel comfortable with this bicyclic system. So here with the downside, it will be, with the downside it will be steric crowding. Okay, with the above side it will be less steric crowding. Okay, so it will be going to add above the plane. Okay, so this is what. Okay, so if you are not able to write the carbene system, you need to recall the chloroform elimination, alpha elimination in presence of the base. Okay, so it's going to give CCl3 minus, which is unstable, leave 1 chlorine. Okay, so it's going to give CCl2 carbon. Okay, so if at all this is there, initially in comparison with the bromine and chlorine, bromine will be a good leaving group. Leaving tendency of the halogens will be greater for iodine, then bromine, then chlorine, and then fluoride. Okay, so bromine will be going to leave first. Okay, so in the next step, chlorine is going to leave. Okay, so both will leave to give CCl to carbon. Okay, so that will be going to add here. Okay, if at all it is chloroform, HBr is going to eliminate and CH2 carbon will be going to form. Okay, so try to recall the carbon formation. Okay, so here it is the example of Simmons-Smith reaction. Okay, so try to hold the name of reaction which are very important for your examination. Okay, so let's go back. So if at all anti-Markovnikov product need to write, so what we have to do, this is a symmetrical olefin, so Markovnikov and anti-Markovnikov rules will not be applicable. So you can write the product in any form. Okay, so both will be going to give one and the same. So So here I have written two regio isomers which are not exactly called as isomers, because if I rotate this ring, it will be going to give this. Okay, so both will be the same. So whenever symmetrical olefins and symmetrical reagents are there, then Markovnikov anti-Markovnikov rules will not be applicable. Okay, so it should be unsymmetrical alkane, it should be unsymmetrical reagent system. Okay, so this is about the workouts based on the free radical reactions. Okay, so next we are going to follow the electrophilic substitution reactions workouts. Okay, so in the last class we discussed about the electrophilic substitution reaction. So it's going to happen in three important steps. So first step, formation of the electrophile; second, formation of the sigma complex; and third, for formation of the products by the elimination of electrophile. Okay, so here the question is, select most reactive among these two. Okay, among A and B, which is most reactive. So to to be readily attacked by the electrophile, or to catch up the electrophile, the system or starting material must be with more electron density. Okay, must be with more electron density. So whenever a donating group, okay, so whenever donating group, NH2 is a strong donating group, I have suggested that everyone must be noted the strong donating groups, or strong activating groups, moderate activating groups, weak activating groups, okay, weak deactivating, moderate deactivating, and strong deactivating. Okay, based on that, regioselectivity is going to happen, directive tendency is going to happen. So everyone must able to recall all the functional groups based on their donating tendency or based on their activating tendency. Okay, so among NH2 and NR3, NH2 will be more donating, so electron density on this will be more, so it will be more reactive. Okay, so aniline will be more reactive when compared to anilinium ion. Okay, so next, among CCl3 and CH3, CH3 is a good activating group when compared to CCl3. Okay, it is a deactivating group, so reactivity will be more with the toluene system. Okay, so among fluorine and chlorine, okay, so fluorine is more electronegative and more withdrawing in nature, or more deactivating in nature when compared to the chlorine. Okay, so these are weakly deactivating groups. Okay, and they are having plus M effect, which can increase the electron density through mesomeric effect, and which can decrease the electron density through inductive effect. Okay, so activating deactivating tendency majorly belongs to the inductive effect, which can decrease the electron density through inductive effect. They are called deactivating group, which can increase the electron density through inductive effect. They are called activating groups. So electronegativity of the fluorine will be more, so it will be more deactivating type when compared to the chlorine. Okay, so this will be more reactive. Okay, next, which of the following is not orthopara directing? Okay, so what kind of groups are orthopara directing? Which are donating groups, or electron donating groups are orthopara directing. Okay, so this is a withdrawing group. Okay, and this is a withdrawing group, strong withdrawing group, and this is also strong withdrawing group, this is also strong withdrawing group. Okay, so all withdrawing groups will direct the incoming group to the meta position. Okay, so all, it's not orthopara. Okay, next, which is not a meta directing. So all withdrawing groups are meta directing. So all donating will be orthopara. So it is a donating group, moderately activating. So this is also moderately activating. Okay, so this is also weakly activating group. Okay, so if it is a phenyl, it is also weakly activating group. So all will be orthopara directing but not meta directing. Okay, so in the last class I have given the list. Okay, so if you couldn't find the list, go go with the previous session. Okay, so there you can find the list of the groups. Okay, so that you can direct the incoming groups based on their donating and activating tendencies. Okay, that class is very important, so refer the last class. Okay, based on that only you will be going to write down the products. Okay, so that's all about the workouts. Okay, so now we're going to begin some more electrophilic substitution reactions. Okay, so the first one is halogenation. Okay, so addition of halogen to starting material is called halogenation. Okay, so we are dealing with the electrophilic addition. Sorry, we are dealing with electrophilic substitution reaction. Okay, so basically to attack the electrophile, it must be electron rich system. So benzenes are the most common electrophilic substitution reactions giving substrates. Okay, so if a benzene is treated with halonium electrophile, let me write the X plus halonium electrophile, then it's going to attack the electrophile, resulting will be the carbocation and the benzene system. Okay, so as the electrophile is attacked, okay, so it will be going to form the sigma complex. So what is sigma complex? It is the resonance stabilized carbocation of the benzene system with equal energies to result or to increase stability in different forms. Okay, so this is called sigma complex. Okay, so why it is called sigma complex? Because it's going to generate by the addition of sigma bond with the electrophile. Okay, so these are the three different sigma complex or resonance molecules that are derived from the carbocation. Okay, so once the hydrogen which leaves as the electrophile results the substitution of the halogen. Okay, so this is about the product. Okay, so how to make the halonium ion? So generally halogens, if I take HCl, H plus and Cl minus will be going to form. So basically halogens are more stable with the negative charge. So how to make it? It's very simple. So how we have done the benzene carbocation? Okay, so how we have generated the carbocation and the benzene? Simply we made reactive with the positive ion. Okay, so when a benzene reacted with a positive ion, it's going to give the carbocation and the benzene. Okay, so when an electron deficient system is going to react, the upcoming or resulting molecule will be with less electron density or electron deficiency. Okay, so if the reagent have electron deficiency, the resulting product will also have electron deficiency, or the intermediate will also have electron deficiency. Okay, so what I mean to say, if a carbocation is reacting, the intermediate will be carbocation. If a carbon ion is reacting, the intermediate will be carbon ion. Okay, or if a electrophile is reacting, resulting will be electrophile. Okay, because both are having positive charge. Okay, if a nucleophile is reacting, the resulting will be nucleophile. So here I need chlorine plus, okay, or halonium plus. So I need to treat chlorine or halogen with the Lewis acids like this. Okay, so AlCl3 is the Lewis acid. So it's going to become AlCl4 and Cl4 minus and Cl plus. Okay, so how it is happening is chlorine will be homodiatomic molecule. Okay, so it will be going to attack on this because it is a Lewis acid, will be attacked by the nucleophile, so it's going to become AlCl4 minus and this bond will be with this So it's going to become chlorine. Okay. So generation of electrophile is the first step in the electrophilic substitution reaction. So that generation will be going to happen by the halogens with the combination with the Lewis acid. Okay. So whenever you are writing the electrophilic substitution reaction in the halogenation reactions. Okay. So whenever it is the halogenation reaction, it must be with halogen with a Lewis acid. Okay. So that it's going to give halonium electrophile, which is going to stabilize by the sigma complex. Okay. Finally leads to the product. Okay. Is it so simple? So let's go with the peculiar examples. Okay. So if I try to make chlorobenzene, okay, chlorobenzene. So I need to take benzene and chlorine in presence of the AlCl3. Okay. So Lewis acid. So general Lewis acids will be FeCl3, AlCl3, ZnCl2. Okay. FeBr3. So these all are Lewis acids. Okay. So BF3. Okay. So note down all the Lewis acids. Okay. So whatever may be the Lewis acid, it's going to give the electrophiles only. Okay. So try to write the products of the halogenation. So today workouts will be little more. Okay. So because you need to perform many examples. So fifth question, try to synthesize the final outcome. And so think logically, okay, based on the directing tendency and activating tendency, okay. So here I want to give two suggestions. First one, Lewis acid will be the Lewis acid, whatever may be the Lewis acid you are using, okay. It will not change the substitution. It will not change the halogenation or halogen that is going to add onto the benzene, okay. So first point, okay, that you must note down. Second, whenever two substitutions or three substitutions like this, it must be directed by the already present group. So you need to observe the uh, groups that are present. Are there activating tendency? Are there directing tendency? Based on that only it's going to happen. Okay. So be careful with the products. Okay. So this is the first workout for you. Okay. So hope you note down. If not, take a screenshot. Let's go with the next type of electrophilic substitution reaction. So let me give the exceptions for the halogenation. Here itself it's going to finish. Exceptions means whenever a strong activating groups, okay, strong activating groups like OH and NH2 groups are there. Okay, these are strong activating groups or not? So when a strong activating group is there, what it performs is it's going to increase the electron density heavily or extensively. That's why we are calling it is strong activating groups. Okay, so when it is a extensive increase of the electron density, it's going to attract the electrophile more. Okay, so it will not stop by the attracting the electrophile with a single electrophile. Okay, so it's going to take up the electrophiles repeatedly. Okay, so resulting is what generally with the bromine, if I do bromine FeBr3 with influence of Lewis acid, it should go to the either ortho position or para position. Okay, so when it is ortho position, it will be more stable because it is going to form hydrogen bonding. Okay, so this is called mono substituted product. Okay, mono halogenation or mono substitution. Okay, so but the thing is mono substitution or mono halogenation is not going to happen and it's going to react for further because of the strong activating nature of this OH group. So it's going to give tri-substituted or tri-halogenation product. Okay, tri-halogenation product. Okay, so if it is a bromine addition to the phenol. Okay, so general reagent we are going to use for the tribromination is bromine water. Okay, bromine water, so which is used for the identification of the phenol. Okay, so phenol's identification resulting into tribromophenol. Okay, tribromophenol, which is ortho and para. Okay, it is because strong activating nature of the voids. Okay, similar to the NH2 group also. Okay, so it is also strong activating group. So whenever bromine water is used, bromonium electrophile is going to generate. Okay, so it is also going to give tribromoaniline. Okay, so this is called bromine water test. Okay, bromine water test. So actually bromine water will be orange red in color. Okay, so bromine water will be orange red in color. So when the bromine completely reacted, okay, are absorbed by the phenol, it's going to give decolorization. Okay, so bromine water test or bromine water will be decolorized when phenol or aniline is present. Okay, or when strong activating groups are present onto the phenyl system. Okay, or benzene. Okay, so this is the exception. Okay, so how to make the monobromo or mono substitution onto the phenol? So you need to treat with the bromine in presence of non-polar solvents, carbon disulfide. Okay, carbon disulfide. So when a benzene or when a phenol is treated with the carbon disulfide solvent and bromine, it's going to give monobromo phenol. In that also there are two kinds of products. One is ortho, one will be para. In the ortho it will be hydrogen bonding, so it will be more stable. Okay, so these are repeatedly asking questions. Okay, so you need to be careful. Okay, so is it possible to iodinate? Okay, So means we have discussed the chlorination and bromination. Okay, so if it is iodination, okay, so simply if I treat with iodine in terms of AlCl3 or any Lewis acid, so we are going to expect the iodobenzene, but it is not going to happen because iodine what is used will be little bit reducing in nature. Okay, as the reducing nature increases, when periods in the periods number, if it is going down from top to bottom in periods, reducing nature increases. So iodine is with reducing nature. Because of its strong reducing nature, it will be reversible reaction. Okay, so it will be reversible reaction, so reaction will not complete. So iodobenzene formation will not happen directly. Okay, so for that we will use different metal reagents. Okay, that we will also discuss in the further classes. Okay, so because of the reducing nature, simple iodination from halogenation or electrophilic substitution reaction will not happen. Okay, so for fluorination, simple fluorination will not happen because whenever F2 is used in presence of Lewis acid, there will be H plus release. Okay, so H plus should be replaced. So uh, in the final product we will be going to form the fluorine. Okay, fluorobenzene, but there would be one more fluorine which is going to release attached with the hydrogen, so resulting will be HF. HF formation is most exothermic reaction, one of the most exothermic reaction, so it will be very much explosive, so product will not be stable. Okay, so for that case we will not use the fluorine with AlCl3, we are going to use xenon difluoride, which is a mild fluorinating reagent. So resulting product will be fluorobenzene. Okay, so these are the exceptions for the halogenation. Okay, so the final exception, this is asked in the previous examination, which is with the pyrrole systems. Okay, so whenever it is pyrrole treated with the iodine with the heat. Okay, so here it is going to give per iodinated product. Okay, per iodinated product means all the positions got iodinated. Okay, so hyper reactive. Okay, so this is going to give per iodinated pyrrole. Okay, so per means all positions got attached. Okay, per chlorobenzene, so 6 positions of the benzene is going to attach with the chlorines. Okay, so this is about the halogenations and exceptions. Exceptions are very important because many a times sequential reactions are going to ask by the simple halogenation methods, and direct questions will be asked by the exceptional reactions. Okay, so hold every exceptional reaction because they are repeatedly asking in the previous examinations. Okay, so let's go with the next kind of electrophilic substitution reaction, nitration. Okay, so what is nitration? Addition of nitro group to a starting material is called nitration. Okay, so if it is a electrophilic substitution reaction, nitro group must be positive. Okay, so NO2 will be electrophile. NO2 plus will be electrophile, which is going to attach to the benzene system, and it's going to generate the electrophile. Okay, which is going to form sigma complex. After that, H plus will be eliminated to form the final product. Okay, so try to write the mechanism here. Okay, with the sigma complex formation. Okay, here I am writing directly. Okay, so sigma complex formation and complete cycle of the nitration. Okay, so hope you fill the gaps with the mechanism. Okay, so try to write the mechanism more times because you will never get doubts during the or in the middle of the mechanism when you are writing in the next steps. Okay, so if you are capable to write in less than 30 seconds of in especially this mechanism, you will never get doubts about the electrophilic substitution reactions. Okay, so try to catch the speed also and perfection also. Okay, so how to make nitronium electrophile? It's very simple. You need to treat the nitric acid along with the sulfuric acid. Okay, so in these two, there will be a base and there will be acid, so that H2O will be released. Okay, so from this OH will be released and from this H plus will be released, so it is going to give as a OH minus left. Okay, so let me write the structure of the HNO3. Okay, so this is about the HNO3. Okay, so as the OH minus left, so it will be going to result NO2 plus only. Okay, so when H plus left, it will be going to result HS4 minus. Okay, so this nitronium electrophile is going to attack it by the benzene, resulting into the formation of nitrated benzene. Okay, so as they are both are acids. Okay, nitric acid, the name itself indicates it is acid, and sulfuric acid, this also indicates it is a acid. Okay, so as the name itself indicates the acid, but it is donating the OH minus, means it become a base, and this is donating the H plus, means it becomes the acid. Okay, so what is the criteria of HNO3 to act like a base is just a comparative acidity and comparative basicity. Okay, so remember one thing, it's very important for your conceptualization based on the acidity. Okay, so acidity and basicity is the comparative nature but not the permanent or standard nature of a molecule. Okay, so if you take HCl, okay, it's going to become, or it's going to act like a strong acid, as you know, everyone. Okay, everyone knows this, it is a strong acid. Okay, but when I take stronger acid than this, okay, for example HbF, HSBF6. Okay, so this is a strong acid, I don't remember exactly. Okay, so super acid. Okay, when I am mixing this HCl with this, so it will suppress the acidity of this stronger acid because it is more acidic now. Okay, so it will readily donate the H plus. Now it should accept the H plus because it is going to force with its acidity. Okay, so whenever a strong acid is present with its combination of super acid or more stronger acid, it become weak acid, or it can act as a base because it is forcefully donated, or it's forcefully is going to receive the H plus. Okay, the same thing is going to happen. H2SO4 is stronger acid when compared to the HNO3, so it's going to give the H plus forcefully, which needs to accepted by the HNO3. Okay, so that's why it is accepting the H plus, and which is acting as a base, resulting H2O release and resulting NO2 plus release. Okay, so how a nitronium electrophile is going to generate with the, it is from the HNO3 because of the basic nature of the HNO3 in presence of the H2SO4. Okay, so the combination of HNO3 and H2SO4 is called as a nitration mixture. Okay, nitration mixture. So whenever a compound or whenever a aromatic system treated with the nitration mixture, which is concentrated HNO3 and concentrated H2SO4. Okay, if it is treated with the nitration mixture, it's going to give what? Nitrobenzene or nitro group or nitronium electrophile releasing is going to happen, or nitro group substitution is going to happen. Okay, so one more question, how many molecules of the H2SO4 used per one molecule of the HNO3? So it is 2 moles of the H2SO4 is used. Okay, so overall reaction will be 2 H2SO4 and HNO3. Okay. So first molecule of the H plus is used for the protonation of the nitric acid. Second molecule will be going to use for the H plus uh, for the water formation. Okay. So two molecules of the H2SO4. So it is 2 is to 1 ratio of the concentrated HNO3 and concentrated H2SO4 is called nitration mixture. Okay. So one is for the protonation of the HNO3 and second for the dehydration. Okay. So as H2SO4 is a dehydrating agent, so two molecules of the H2SO4 is used. Okay. So this may be asked in DHA and other uh, simple examination. Okay. So but in the IIT JAM and HCAT examination, there must be mechanistic studies and mechanism based uh, questions only. Okay. If at all regio selectivity based means ortho para. Okay. So di substitution, tri substitution. Okay. So one question may be expected from these electrophilic substitution reactions. So mechanism is similar for everything. Okay. You need to follow either the exceptions or the reagent system. Okay. So let's try to work out the examples. Okay. So here I am giving some more examples or some more workouts. For aniline, there won't be tri-substitution in the nitration because chlorination is going to be a little activating group. Okay, but nitro group is completely deactivating, a strong deactivating group. So once it gets substituted with mono substitution product, also is going to decrease the electron density. So further reactivity will not going to happen. Only mono substitution. Okay, mono. So next. With the pyridine, what could be the product? So you need to see the regio selectivity. Okay. So when it is going to give the tri substitution product is when it is a phenol. Okay. So this is not happening with the aniline, but it is going to happening with the phenol. Okay. So why it could be? Okay. So you must try to think. Okay. So mention in the comments or mention in the group. Okay. So why a phenol can give the trinitro or tri-substituted product? Okay. Why can't the aniline? Okay. So if you couldn't find the answer, I will give in the next class. Okay. So I think this is one of the important question that is repeatedly asked. Okay, in different examination. So aniline only mono substitution, okay, with phenol tri substitution, okay. So this is called trinitrophenol, okay, trinitrophenol, which is named as a picric acid, okay. So one reason is nitration is going to deactivate, okay. So first substitution is going to deactivate it, okay. But the thing is, it's going to give mono substituted, which is meta substituted, okay. Mono substituted, which is meta substituted, okay. So try to find out the answer. If not, we'll be going to discuss tomorrow, okay. So why try substitution with the phenol? Why not with the aniline, okay. And if at all mono substitution, that is with aniline, it will be meta substitution. Why not ortho para, okay. So to make mono substituted product from the phenol, we require, if it is concentrated nitronium ion, concentration will be more, so that we will decrease the concentration of the electrophile by using dilute H2SO4 and dilute HNO3, okay. So it's going to result the mono substituted product, okay. So ortho and para, okay. So try to give the major product among these, okay, which is major, and why, okay. So by thinking about the reasons about the stability, you will be going to get more clarity on the previous selectivity, okay. So hope you will try, okay. So whatever the doubts, you can mention in the group, or you can mention in the comment box, okay. So we will be going to discuss further, okay. So that's all for today, okay. So thank you.